Graph embeddings are useful, but link prediction is where they become a working model. Predict which edges should exist, but are missing. You'll see how to connect the pieces into a workflow that learns from graph links and scores a missing connection. I'm Professor Pi, teaching AI foundations with simple Python. Link prediction asks a simple question with big consequences. Given a network of items, people, or papers, which pairs should be connected next? In practice, this powers friend suggestions, product recommendations, and missing citation recovery. Classic tricks comparing node features or counting shared neighbors miss the broader structure you get when nodes pass messages to neighbors a few times. The practical idea is to learn a vector for every node, so related nodes sit near each other. Then we score a candidate pair by how compatible their vectors are. The key twist: supervision is on pairs of nodes, not on node labels. Training from known links and sampled non-links turns embedding learning into a supervised predictor. We'll build a tiny PyTorch geometric baseline, construct a toy graph, hide some edges, train a small GCN encoder to make node vectors, and score held-out pairs. You'll see the pieces: graph construction, labeled pairs, an encoder, a dot product scorer, and a training loop that keeps held-out edges truly unseen. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we create the minimal graph object we need for link prediction. This snippet builds the smallest PyTorch geometric graph we need for link prediction. The viewer-facing shift is important. Instead of treating examples as rows in a table, the supervision will come from pairs of nodes. X gives each node a simple feature vector, while edgeIndex stores known connections in PyTorch Geometric's data object. The both list adds reverse directions, so message passing can flow both ways on this toy graph. The visible output confirms the graph size before we start hiding edges and asking the model to recover them. We need a way to turn edges into labeled training pairs, so the model can learn what a real edge looks like versus a sampled non-edge. This example turns the PyTorch geometric graph into a supervised link prediction task with RandomLinkSplit. The hidden trick in link prediction is that the model needs positive examples, which are real edges, and negative examples, which are sampled non-edges. Split data returns train data, val data, and test data, each carrying edge label index pairs and edge label targets. Setting is undirected true helps keep reverse copies of the same connection from leaking across splits. The output shows how many labeled training pairs now exist, which is the bridge from graph embeddings to supervised learning. Now we need an encoder that turns node features and the training graph into embeddings while hiding held-out edges from message passing. This code creates a PyTorch geometric GCN encoder with sequential and GCNConv. Link prediction usually does not classify nodes directly. It first learns a vector for every node from the training graph structure. The first GCNConv mixes each node with its neighbors. ReLU adds a nonlinearity, and the second GCNConv produces the final Z embeddings. The model sees only train data.edgeIndex, so held-out edges remain prediction targets instead of message passing evidence. The output shows one embedding per node, which gives us the ingredients for scoring candidate edges. Before we add training, let's see how a simple decoder would score candidate pairs from those embeddings. This snippet scores possible missing edges using the embeddings from the PyTorch geometric encoder. The key idea is simple but powerful. Score edges compares two node vectors with a dot product. Then sigmoid converts that raw compatibility into a probability-like score. Pairs is the candidate list we want to rank, not the training graph itself. argmax selects the pair the current model believes is most likely. These scores are still from an untrained encoder, so treat this as the decoder shape, not a useful predictor yet. The output shows the top candidate and its score, making edge prediction visible. Now we plug the encoder and scorer into a training loop that learns from labeled pairs and evaluates on held-out edges. This example completes the PyTorch geometric baseline by training the encoder and edge scorer together. The loss compares score edges z, train data.edge label index, against train data edge label, so the model learns from both real edges and sampled non-edges. Binary cross-entropy with logits is used before sigmoid, which is the usual stable form for binary link labels. The evaluation recomputes embeddings from train data.edge index and scores test data.edge label index, keeping held-out edges outside the message passing graph. More epochs can fit this toy graph harder, but with tiny data, the test result can still jump around. The output shows held-out edge accuracy for the full mini workflow. This toy pipeline maps to a real project quickly. Swap in the Cora citation network or a small user item graph. Keep the same RandomLinkSplit pattern and scale the encoder depth and hidden dimension. For recommender prototypes, raise negative samples per positive and monitor AUC or precision at 1 to match product goals. Keep 3 points in mind. Link prediction with GNNs learns from pairs of nodes, not node labels. Use it when relationships matter and local structure carries signal. And a single caveat: if held-out edges leak into message passing, your evaluation will be optimistic. So always split edges first and run message passing only on the training graph. To extend this exact build, run the same workflow on the Cora dataset and tune the negative sampling ratio and hidden dimension. Increasing negative samples per positive from 1 to 5 will make the model learn a sharper decision boundary. And growing the hidden dimension from 8 to 32 often helps on citation networks. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.